Okay, the second speaker is Jaeyoon Choi from KAIST, and he will talk about classifying universal protein dynamics in the Spinor Condensate. Please welcome.
I'm the organizer for inviting me this nice workshop. And actually, I have presented very similar experimental result in last year. I mean, CMS do, but I wish at this talk I would update some new results on that, and also maybe some prospect what you can actually try to see out of this nice condensate system. All right, so this is an experimental talk, and I know that after my talk is lunchtime, so I do not want to bother you. We are hungry, so I would try to keep my times on time. All right, before starting, I'd like to thank to the collaborators, and this work is actually initiated by the CMOS at Harvard University, where they propose some experimenters, and we have carried out, which is mostly done by Sun Jung here, and he did a really wonderful job in making this work progress. All right, so motivation for this talk. I mean, in very general, I'm pretty much very interested in my research career is about how these quantum systems, especially isolated magnetic quantum system, reach the thermal equilibriums if you just wait a very long time. I mean, this thermalization behavior is quite familiar to us, right? I mean, it's in the classical system, which you can see in this picture in every morning if you light the coffee. And then you can pour the drinks, the milks, the espresso, and you just stirring up, and you reach the equilibriums in coffees. And this question is being non-trivial if you're interested in, if you ask a similar question in the quantum system, because if the system is isolated, and you know this Hamiltonian will be below the unitary revolutions with these equations, and so there's a lot of chances to find a new physics behind it. And in our communities, what we usually do is about at the settings. I mean, we just first prepare some initial state, well-defined initial state. Like, for instance, imagine that you have like XXC system of Heisenberg models, and you prepare the C of spin-up state. At the center part, you flip the spin-down state. And then you let the system evolve and what's going on after a long time. And this sort of experiments is like, pitches are quite a lot to find out some new discoveries in non-equal system. And the well-known example is, I think, is about Peebles drag mechanisms, which when you're close the phase transition point, for example, temperature quenchings, and the gas in this case is, sorry, I guess the matches up here, across the phase transitions. There is a characteristic scaling of predicted in some characteristic length scales. And also for some kind of special system like integral system, like one-dimensional strongly interactive Bose gases or these spin-XX models, then people actually find out some non-thermal behavior. And even this non-thermal behavior actually can be described by so-called generalized Gibbs ensemble, where they introduce additional integral motions in the dense matrices. And also people have dared to ask whether these kind of thermalizations can be prevented in some system, I mean, even for the strong interactions. And we have, now we can know that there's some phenomena of a dimensional localization, which is well established in 1D and still a bit debate in the two-dimensional system. But still, all of the system is basically asking the questions about what is the fate of the many-body quantum system when the system is really far from equilibrium system. And then you can actually think about a variety of the scenario. As you can see in this picture, well, the first one is something like without relaxation, they're just keeping going on with this one Hamiltonian. And the other one will be just relaxed down into some sub-equilibrium state with just single time scale or some multiple time scale, well, something like this one. And out of these situations, my talk is more or less focused on the questions about if the system reaches thermal equilibrium, can we somehow find some universal features on their way to reaching thermalizations? Or if it is, can we classify its universality classes? And if we can do, what is the the critical aspect that you have to thinking about when you want to classify this non-equal dynamics. So these two questions are the basic question that I like to address. And there's motivation for that because in the system, we already some example of that, which is the coarsening dynamics. As you can see in this picture, in this is to immiscible fluid as the time goes on, you can see the characteristic length scale actually increasing over the time. And if you plot this length scale, the character length scale over the time, they can actually find out a characteristic polar behavior. And depending on these polar exponents, people are already categorizing their dynamics. And this dynamics is actually happens, it's not very far from equilibrium, but it's quite close to the sum. But still, they have bunches of different classes, depending on some critical exponents or physical models here. And so the question is, can we also explore similar stuff in a closed quantum system? And indeed, there is some kind of pioneers who actually propose and numerically propose this kind of can be possible, mainly by the Heidelberg group under the name of so-called non-thermal fixed point theory. And this picture shows some kind of initial condition here, which is highly non-trivial, a non-thermal state. And if you just wait a long time, and you can see some characteristic distribution, this is actually momentum distribution, but it doesn't matter. Whatever it is, if you find some suitable physical observable and rescaling its amplitude and time wise, then you can actually see beautiful collapses onto a single curve, which signifies scaling behavior. And then they have actually formulated how this can happen phenomenologically. That's by the new names of non-thermal fixed point, just like a fixed point in the equilibrium phase transition point, as the initial conditions really goes far from equilibriums, they are some kind of artificial, some fixed point that maybe exists, such that the path through the thermalization follows the universal curves or the scaling, and also follows the scaling behavior. And such kind of theory has been tested about a few years ago in different groups, Heidelberg and Wien and also Cambridge. They also different systems, but they exhibit quite similar spatial temporal scalings by measuring the spin structure factor or momentum distributions and so forth. And all the functions can show that these some kind of observables can be scaled down into some two scaling exponents, the amplitude and characteristic length scale with that help. However, the problem is their experiment has a big gap between the theory. Especially in particular one Bose gases, there's a factors of 5 difference from the installations, and also it has Heisenberg's one distinct system also, so the theory is a bit away, which means we are not fully understand what's going on in the system. And so the question would be then why we're missing and what sort of the natures are hidden to determine the scaling exponent in these cases. So that is main motivation for my talks, and my outline is as below. I like to show because I guess my experiment platform might be not so familiar to you. So I'd like to introduce what is the Spinor condensate, and then I would like to show 2 different experiments. One is the domain coarsening with Ising symmetries, and the other one is the SOC matrices. Okay, so first, I'd like to introduce my experimental platform, which is highlighted in the physical research about 3 years ago. We are using the cold atom gases, and cold atom gases are actually trapped or produced inside these vacuum chambers in here. And we collect the bunches of cold atoms into a well-defined localized space by using these well-focused laser beam. And this laser beam can collect these bunches of atomic clouds and reaches temperatures about a few tens of nanokelvins. And our atoms have integer hyperfine spin state, for example, F=1 state in here. And so we have 3 so manifolds, spin up and down as a state. And this potential, the optical potential, is actually spin independent. So you may just consider that the atoms are really just collected charges by the single Hamiltonian connections. And what is the Hamiltonian then? What is Hamiltonian throughout the system? Well, Hamiltonian is quite well described by very simple Hamiltonians. I will show you. And the interaction is actually the van der Waals interaction between the atoms, as you can see here. And at low temperature, at ultra low temperature, these interactions can be characterized so-called the S-wave scattering lengths with a quantum interaction form. And of course, if you have introduced the intrinsic spin degrees freedom, you can have different spin collision channels. For example, the spin 1 and -1 and combine into going into spin and -1. But also you can have some kind of spin mixing that these two spin zero collisions are produced spin at up and down spin state to preserve the angular momentum. And in a sense, our interacting Hamiltonians can be expressed into two different coefficients, C0 and C2, where the C2 actually represents this kind of spin-spin interactions. All right, so that is our Hamiltonians, and there's one mark here is about these processes, these spin mixing processes, is in the order of scales of the spin interaction energies. C2 coefficients times the densities is called, I'll call it spin interaction energies. And typically these liquid gases, it's, as you can see in this picture, this is the order of 100 or 200 milliseconds. Please remember that this is quite a long time, and this actually, because of the fact that spin interaction energy is quite small. All right, and then maybe your question would be then what is ground state and what is the phase diagram of these Hamiltonians? And it's quite straightforward to see because we can see that these magnetizations of this Hamiltonian will determine the sign of the C2 coefficients, right? If the C2 is positive, then you can easily expect that the spins will tensor line or maximize its directions. So we call it as a ferromagnetic phase, just like the rubidium atoms, 87 atoms. And in other ways, if the C2 is positive, then you will favor to have the spin length become to 0. And we call it as polar phase. And that is the case for the sodium 26. And additionally, we have additional tuning knobs to that shows the rich phase diagrams, which is the quadratic Zeeman energies. Here, I think it's a bit different, but it's quite very, very simple pictures. When you apply these magnetic fields, there is two things. The first one is Zeeman energies, which splitting, oops, picture is a bit wrong, which small magnetic fields is the energy splitting linear with respect to the applied magnetic fields. However, up to certain points, because there is some rapid crossing over the upper hyperfine state, there is a banding structures appear, which means that there occurs this so-called quadratic Zeeman energies. In other words, it simply means the atoms in spin 0 state are more favorable compared to spin -1 and +1 state. So we can say if you apply the magnetic fields, in this case, our magnetization is so-called always preserved, it's a closed system. So for small magnetic fields, that if you prepare spin 1 and -1 state, they're still preserved. But for a very strong magnetic field, because of the quadratic Zeeman energies, the lowest energy will be given by spin 0 state, that the spin population will go to spin 0. Then you can immediately see from this picture that there's two competing energy scale, for example, especially for the ferromagnetic phase, because I said that for the C2 is negative, for the ferromagnetic phase, it favors these maximized spins. But if you increase your magnetic fields, the quadratic Zeeman energy will dominate it, such that the spin length becomes a 0 state. Right? So there's two competing energy scale, and therefore you can actually expect some kind of phase diagram quotes. And that is phase diagram for the Spinor condensate, for in the parameter space spin interaction energies, and quadratic Zeeman energies. And as you can expect, for very large quadratic Zeeman energies, Q is large, then the ground state is polar phase, where the all atoms is just populating the spin 0 state. And in the cases for in the third quadrant here, where the spin interaction is a negative and the Q is negative, it means the Q is negative means the one over this state will be favored over this spin 0 state. So you're trying to maximize the spin by aligning all the spins +1 and -1 state. So that is basically the phase diagram of our system. Quite simple. And traditional platform of this BC is about rubidium for the ferromagnetics and sodium for the antithermal or polar condensates. And the one differences between the system from ours is that this system is rather a weakly interacting system in a sense that if you compare the ratios of the C0, which is the spin-independent interaction energies, and C2, which is the spin-dependent interaction coefficients, their ratio is quite small. It's about order of percent or less than 1%, for example, in previous cases. And that is actually combinations of scattering lengths for different scattering channels. You can actually see there's a bunches of calculations and measurements. What you can actually find out is, except this lithium-7 atoms, in these cases, it predicts actually about, compared to the lithium atom, is about 100 times stronger spin interaction energy. It's quite attractive atomic species. But as you can see here, there's no error bar, right? There's no error bar. It means that it's not measured until 2010, which we did. And so, our motivation when I began the experiment, we are trying to realize this Spinor condensate using the lithium-7 atoms because it favors the strongly ferromagnetic spin interaction energies. And that actually lead us take advantage of exploring very long-time dynamics because of this strong spin interaction energies. All right, so apologize that I skipped the details about how we realized. Yes, please.
So in your experimental setup, do you have any writing or distillation, or do you not take those into account?
Okay, we have, of course, our experiment is not fully 100% isolated system. We have kind of.
I'm asking because scenario with which you are comparing this burger scenario, I think. Do they have some, like, do they provide that it will work for certain type of systems, like the driving and dissipation that you have in your system? Maybe those are important. Maybe those will push you on the universality.
Yeah, dissipation is quite important in terms of when you, I mean, for example, if the coarsening, for example, in these cases, is driven by the topological defect like vortices, and the dissipations would affect the dynamics of the vortices in a certain way. And in that cases, of course, it matters. But in our cases, the dissipations is on and off. I mean, it always compared with the time scale which you are looking for, right? In general, time scale is about 10 seconds or the order of this one. And our experiment I will show you, but it's not about 1 second. So we know that the dissipations occurs, but yes, such kind of different, separable timescale relaxation dynamics, coarsening dynamics may have quickly affecting the dynamics of the coarsening.
One more experiment. So how many atoms do you have? Do you have like linkage of these atoms, or they stay the same?
We have roughly 3 million atoms. Yeah, 3 million atoms. But of course, in every different realization, we have different atom numbers, and the uncertainty is about 10%. We have about 10% fluctuations of the atom numbers. Okay, good. So I'm not sorry that I cannot introduce the more technical details how we realize these lithium-7 condensate or Spinor condensate, because I think it's too technical, but please believe me. I also showed some real picture images, so there is. All right, and also one important thing is we are actually the chemical potential, the midfield interaction energy of the condensate is smaller than the tight confinement of our optical potential, which means in the vertical axis is only the single mode, which means there's no spatial dependence on the vertical axis. In other words, our condensate wave functions can be described by X, Y, or the two-dimensional system. And out of that, we actually perform the spin oscillation experiment, which is about this one. The spin populations are oscillating back and forth. And you can see this time scale is about a few milliseconds, which is way faster than the atom platform, the living condensate, just because of this strongly spin interaction scales. And more formally, our typical characteristic timescale for the spin TS is about 0.5 milliseconds. And as I told you before, in our experiments have been carried out about a few seconds. For example, 1 second gives about 2,000 spin collision time, for example, and not just 1 second. That is actually main advantages of our system. And I guess that is main reason why we can explore much longer timescale dynamics compared to the other experimental platforms. All right, so this is our experimental setups. Sounds like quite a bunch of optical systems, like some garbages, but if you carefully find out, actually there is some kind of shiny vacuum chamber that actually atoms boils up and going through here, and that is our main chambers where we pull the atoms by trapping using laser light. You can see the reddish fluorescence light because you are using the 7, you know. And cool down the atoms further, you can actually see the Bose-Einstein condensations, the poolings. So yeah, we have made it. And the next thing is exploring the coarsening dynamics in a Quench system. Sorry, it actually posted it on the archive a few months ago. So our experimental system, is like this one. We first initiate our initial state in a polar phase Q in here by increasing Q value at some positive values. And then we rapidly quench this Q value into some where Q is negative. And the Q is negative, I showed you that the ground state is either spin up or either spin down state. And it has the Z2 or the Ising spin symmetries. And also you can expect as a defect as a domain voltage. And or we can also quench the system into Q equals 0 points, which means it is isotropic ferromagnets that you have only your Hamiltonian only at the spin-spin interaction steps. So in that cases, it has SO3 symmetry, and your topological defect is so-called the Z2 spin vortices. And our experiment will I will show you that we perform the coarsening dynamics in 2 separate regions, the z-axis and isotropic ferromagnets, and we find that the scaling exponents, I mean the characteristic exponent that the wavelength grows are actually different, and there is a strong evidence that this is actually mediated by the annihilation dynamics of the topological defect. For example, the experimental 1 cases is the domain role, and experiment 2 for the isotropic ferromagnets is more related to the annihilation dynamics of the spin vortices. That's actually the main messages for my talk. All right, so yeah, that's the experiments. We have first prepared all the atoms in the spin 0 state, right? So we are capable of taking images for all spin subsystem at the simultaneous speed. And then we wait a little bit. At the very beginning of Quench, we see minus and plus 1 state are generated out of this 0 state, and that is actually comes from the dynamic instabilities. I mean, our initial state in this case is not stable, and when the Q is negative. And this is just like you put your balls on the top of the hill. So small quantum fluctuations just goes away into producing the correlated spin of minus pairs. Yes, this is a small one. So but at some very long time dynamics, let's say 200 milliseconds, you can see there's no population, almost no populations of our spin 0 state in the condensate. Right? And while you can see this spin minus 1 and plus 1 state still remaining, and it seems like their size are actually being increased. And indeed, we can analyze the coarsening dynamics by extracting magnetization densities mz, which is represented in these pictures, and it clearly show the coarsening dynamics. And to characterize or to quantify the characteristic domain lengths, we use the spin-spin correlation functions, which is defined in this way. And as you can see, it's quite largely isotropic. So we take the larger averages of this spectrum to get profiles, and that is how we look like. And as you can expect, there is a negative correlation just because there's spins up and there's some distance, there's spin down states. And that is data point for 200 milliseconds. And if you wait long enough, then you can see this domain, the characteristic domain size are actually increasing over the time. All right, then the next question is, can we find some scaling behavior of these correlation functions? And to do that, we define the domain lengths as the cases where these correlation functions are meet the 0 crossing in here. And then we can find what is domain lengths for each whole time, and then we can normalize or the least scale the positions are by respect to these domain lengths here, and we find a beautiful collapsing of all the different data points. And furthermore, we compare our numerical simulations with using our experimental parameters, which also lies on the top of each other, with it very good enough. And the next question is then, the key question is then what is the power law exponents for the domain lengths? Is about this one. Yes, yeah, this is our experimental result. And again, if we plot this on the top of our data with the numerical simulation, it also shows a good agreements. And to get the exponents, we this one of the z exponents, we take a log plots of these data and make some linear fits. Yes.
Why are those installations?
Yes, thanks. This is just because we do the quench and we are harmonic trap. So there's some breathing motions back and forth, and naturally the main lengths are actually shrinking back and forth. Yeah, thanks.
So this numerical simulation just quench dynamics, with unitary dynamics, just Hamiltonian.
Yeah, the same way. All right, we get the experiment. We get the logarithmic plots of this one, and we get about 0.6. And that is actually quite good agreement with the simulation result. We're not so surprised, but our surprise is that this is actually a bit smaller than what people has been predicted.
It's the total length of domain. What is L?
The L, I define the L as from the correlation data here. Let's say you get the correlation functions of G of R, then we extract these lengths L when the correlations meet at 0 process. Yeah, just because to follow
the size of the domain.
Yeah. Yes.
You show that numerical simulation. Is it done for t equals 0?
Yes.
How did you handle that initial fluctuation? Because I think that determined the initial.
Yeah. They can make some random fluctuations sitting inside the simulations.
But the magnitude is kind of t equals 0.
You mean absolute equals 0?
Yeah.
No. There's a finite about few percent of fluctuations. I don't know exactly to understand, but what I'm saying is about epsilon is about 0.1.
Because your sample is very big in 2D region, so I wonder there's additional fluctuations.
Yeah. That's a good point. Yes. I can tell you the latest about this. Actually, yeah, I can tell you here. Actually, after this paper have been posted on the archive, there is some theory, numerical theory, that these exponents can vary on the temperature because the thermalization can also lead this kind of forcing dynamics, and in that case, the exponents actually being affected. Yeah, it's changed. Yeah. Okay, so I have run out of time. Okay, so yeah, the problem is, our finding is a bit still disagreement with the previous studies where they predict about 0.68 or 0.7. And more precisely, this is actually comes from, you can actually get some insight of this exponent from these hydrodynamic equations. And in these cases, for the binary fluid cases of this hydrodynamic equation predicts 3 different characteristic regions. For example, for when there's no mass flow, we call this as diffusive with exponents of 1/3. And for the viscous hydrodynamics, you expect this exponent to be 1. And inertial dynamics, when the viscosity is 0, one expected to serve. And in these cases, in our system, we have superfluids and binary cases. And of course, the mass flow has to be exist, such that our system is quite natural to expect the dynamics for the inertial hydrodynamics. So why we have some kind of 10% differences? Well, we consider this one actually comes from the finite size effect. More precisely, this experiment has been done with a very, very large system size, about 800 spin lengths, and up to about 10 to the 4 times, 10,000 spin diffractions. And there is actually some studies that if you have system size of finite, and these exponents actually become a deduction and reductions of the system size. And let's compare our data where we are, for to say, I said our characteristic time scale is about 0.5 milliseconds, and this is our spin healing length, which is about 2 micrometers. And if you do that, our experiments, our time window is about these regions, which means some kind of these are small windows, not in the very, very large system limits. And if you just extrapolate this result in here, we actually find a bit, it's about quite close to 0.6. So maybe this is actually comes from the finite size effect. And of course, there's also experimental issues, which is related to imaging resolution. Because it is something like if the domain size is very small, then we actually lose the signals of small domain, which actually affects the time exponents. And to characterize this one, we have characterized what is imaging resolutions. We get about 5 micrometers, and we take some deconvolution method and get a little bit of enhancement, but still small compared to thermodynamics. And this kind of exponent can be also seen from the domain of numbers. I mean, we can actually count the domain of numbers in here, right? And domain number, we can actually expect that this follows of this scaling with the fixed radius, then it actually has to follow this kind of scaling exponents, which is twice larger than this because of this scale. So we try to investigate these power scaling functions by just counting the domain number, which is like this one. This is a full-time evolution dynamics of the domain number from the beginning and the end. Yeah. At the beginning, of course, this coarsening starts and it's dry to peak at about 200 tens of milliseconds. And there is actually still m equals 0 component still going on. And after around that point, the coarsening stage starts. So we set this early time dynamics as before the 100 milliseconds, where the 0 component still exists. And after here, reaching the 1 seconds, it means there are only few domains, only 1 or 2 domains. So there's nothing going on. And after noise, the domain size actually can decrease because, as I said, there is some relaxation heating processes going on the order of 7 seconds. So we choose some time intervals on between to get the exponents, which gives still about a point, a bit large error, but still around 0.6. So we get something exponents that are quite similar to the inertial domain regions. And the next thing is, can you see that it's actually independent of each other? And we perform many different initial state, and especially for a different initial spin composition of and minus 1 state, the dynamical instability is totally different from the polar phase condensate. And in these cases, we expect, and we see the immiscible phase separation dynamics between the spin 1 and minus 1 state, which is also, you can see the coarsening dynamics in these cases. And we can also do the similar analysis with the different time zones in here, because it happens a bit more earlier. And we've also find a very nice collapsing data on the single functions. And this single function is actually well agreed with the scaling function that you already obtained previously, which means even with a different energy condition and setting, they are scaling the same exponents. And that's basically the summaries of the easy access coarsening dynamics, where we have various different initial conditions. And this open symbol means before the deconvolutions, and the blue one is after the deconvolution, which increase a little bit. But both data is clearly far away from the other, for example, this viscous or this diffusive region. So we consider it can say it can be classified into the inertial or hydrodynamics, or in the classical field in model H. Okay, and the second part, how many times on that? 5 minutes? Okay, yeah, it's also simple. It's very similar. We just quench in a different region, Q equals 0, and do the same experiments. And in these cases, people expect, of course, a different scaling exponents, because in the cases the vortices are involved, or precisely spin vortices. So the spin vortices are decreasing over the time, where the characteristic time scales t to the minus 1 in these cases. And the characteristic length scale is actually t to the 1/2, so it's a 0.5. And of course, our window is a bit smaller in here. And as you can see, because it also induced some kind of finite size effect, because the exponent is a bit slow. The slope is a bit is not steeper than this 1/2. So yeah, we try to address the questions about, can we see this kind of scaling behavior when we quench these spin isotropic? And that is our result for the law data for the isotropic quenches. As you can see, this is actually the magnetization along the z-axis, and that is a magnetization along one of the horizontal, the mx axis. In contrast to the previous z-axis phase, we see the coarsening happens in all different spin axes because it's symmetric points, so it should happen all the time in all different spin axes. Yeah, and we do the same. Yeah, basically follow the same analysis tool to get the scaling function, which agrees quite well, and also the scaling exponents. And in these cases, we get about 0.43 for different axes, which is of course quite smaller than the 0.5, but just because of fine size effect. And can you see? Then the next question is: can you see is, or can you associate this dynamics as the this kind of vortex dynamics? Right? This is so-called one of the spin vortices. These two spin vortices, where we can see the spin windings of -1 here and +1 here. And to find the signatures of the spin vortices, we take a meta-wave interferometries, which is like this one. Here, this is a component for -1, 0, +1 state that representing this spin vortices. And then we apply the RF pulses. What does RF pulse do? Here is it can split, or the transfer is population into the other spin components, -1, 0, and +1 state. And this is same for the spin 0 and spin 1 state. Okay. And now we can see, especially for the spin 0 state, you can see after the RF pulse, you can measure the relative phase between the spin -1 and +1 state, right? Like in these cases. And same for the -1 and +1 state. And that is actually quite well-known techniques in our communities, and also the techniques that detect the optical vortices and optical vortices. And to enhance the visibilities, we applied additionally the phase gradients along top of each other, which means in every time you close the black line, it means it's close to 0, 2 pi, 4 pi, and 6 pi, and so forth. And that is the case without any phase singularities. But with a phase singularity, you can expect there has to be some phase jump across 2 pi phase windings. So you can see the number of fringes are being different compared to here and there, which signals the phase singular points. So we try to find some signatures of Y shape or fork shape to identify this vortex structure. And that is how we obtained an experiment. When we take the images before the density, we apply the RF pulse, and that's how we observe. Here you can see clearly the Y-shaped pictures, which is also agreed with in numerical simulations, or sometimes a fork shapes here, which signals the spin vortices. And sometimes you observe this kind of H-shaped patterns here, which means that the vortices are quite close to each other. So we assign this one as a vortex diapers, and we analyze the statistics, such that the vortex number and the intervortex distance. This solid line is the fit line to this local fit lines to this vortex number and intervortex distance, which is actually good agreement with about 0.4 scaling exponents, which means that this dynamics is mainly associated with the annihilation dynamics of the spin vortices. So the conclusion is we have performed the coarsening dynamics in 2 different symmetry, ground state symmetry dynamics. Because and find that the relevant topological defect is quite crucial, play a crucial role in determining the critical exponents. Yes, and as an outlooks, this is the new slide that I made yesterday, but discussion from the professors coaches here. Maybe you can also suggested maybe you can also find some interesting scaling by counting the statistics of domain wall. And of course, we can also explore some strongly correlated system like the spin-1/2 high-sensitive models, where they also predict some kind of non-thermal fixed point behaviors. As an ongoing work, I like to introduce also, we have also investigated Kellenhoff's instabilities, where Professor Takeuchi also showed yesterday. This is 2 domains, up and spin down state, and we can drag these spin domains, and we observe this kind of characteristic features of patterns, which is quite frequently appearing in our natures. And more than that, we also see this kind of generations of these Skolmian-like tips, where we can see 2 consecutive images of magnetizations with a time intervals of 2 seconds. Indeed, you can zoom in this region, you can actually clearly see that are actually detached from these tips in here. And also, we sometimes see the larger domains, one single domains, sometimes split into 2 isolated domains, which maybe signatures of eccentric fractional solvents. Okay, so to that end, maybe I could introduce these talks, maybe if you invite me in the next years about this calculated instabilities. To that end, and thanks for your attention, and thank you.
Thank you for the nice talk. Let's have a couple of questions.
I mean, quickly, very naive question. I probably missed it. So the line shape of the correlation, the spin correlation, and then I guess I didn't really understand why does it go to negative.
Just because it means, maybe I can show you the exact formula. Oops, sorry. Yes, you should multiply these MZ magnetizations and with respect to some distance interval. So
I mean, I can understand the definition, but so that means that at certain distance you have a
negative correlation.
Correlation. And why? I mean, I guess that I'm asking about the physical. It's because I think in sort of more regular magnetic system I'm familiar with them. So it's just decays like exponentially or something like that. But why does it decay like going into negative and then go back?
Just because if you are going further, there is also different domains nearby. So it will displace an oscillating behavior back and forth because you have, for example, if you multiply this one, displace and meet become negative correlations. But going further, you can also see additional correlation, positive correlations.
So then why does it come back? Like it's not also, it looks like it is sort of very.
Of course, yeah. Just because we are averaging so many data, it's oscillating. The oscillation, you can also see a bit of small oscillations in here.
So it actually does go positive and then.
Yeah.
Okay.
I have a question about the principal cubical cell. I'm not sure about spin vortex in that case, but what is the size of a single spin vortex? It's safe.
Question. Yeah. We can, okay. Let's say. We cannot actually measure precisely the core size of these vortices because what you get the image is something like this one. So it's difficult to assign where is the core of this vortice, even without time, even with the time. So what you can actually rely on is rather just directly measure the density depletion core, but rather relies on the this kind of interference changes.
So basically, as the initial pattern can be related to the result of separate analysis of the initial instability, right? Then the vortex density can be done by such a result. But in the as you saw the Blaze review, traditional understanding is the thickness of the vortex should be much smaller than the larger in your case. Characteristic distance between character size of domain. So
it's larger than
So I wonder what happened in your case.
Well,
you observe many OC or I don't understand.
Of course. Yes. Here, I do not bring up the numerical result. Here, we typically observe maximum number is about order of 10 vortices. And the size in this case is only time. So, and you can also see the intervortex distance about 100 micrometers. But of course, this is a bit underestimated because, what our measurement of this vortex is assigned by how much can we see these fork-shaped patterns. If the vortices appears on the same line, very close vortices, then we cannot actually detect these vortices. So along with this experimental result, it's difficult to really find out what is the characteristic distance between the vortices. We are just show this lots of scaling over the time.
So I think I missed this point, but I mean, how does the finite side effect on the forcing dynamics for SO3 symmetric phase compared to that of the Z2 symmetric phase. And you discussed at length about the finite Fourier effective for Z2 symmetric phase, but I mean, what's like the
Well, we do not actually study details what is the final size effect. We just guess because even for these original proposals, you can actually see already in this graph, right? And here the exponent is a bit weaker than in these cases because it's in all different dynamic stages. And if you fit in this region, it's actually quite close to our 0.4. And in that regard, I guess I suspect the previous experimental result where they see the big deviations from the theory just because they're actually maybe not really entering in these real universal regions in their experiments because the time scale is not enough to explore much longer time scales.
I have one question. You are talking about SO3 symmetric phase, but in that manifold, we cannot define the spin vortex.
Spin vortex?
Without any spin anisotropy, spin cannot be confined in the plane at all. But once you have a spin vortex, it can be moved to the point in your sphere, right?
But it can also have singular spin vortices, right?
But without any spin anisotropy, we're talking about the full isotropic situations, right?
Yeah.
In that case, I mean,
But I think the first homotopy of the SO3 is Z2, not 0. Right? So
second homotopy.
second homotopy may 0. Yes, second homotopy may 0. Yes.
Yes. Okay, if there is no further question, let's thank the speaker again.